So now we need to move to the second shape of nuclear fuel. We're going to talk about the cylindrical fuel. So the three-dimension drawing of the fuel, it's a cylinder. That's a fuel pellet. Again, center line is here. This is where the coordinate R is measured, and the total length of the fuel, or the total height, is L, and the outer radius of that fuel we're going to call the R capital, or you want to call it R fuel, call it R fuel, that's fine. The problem again that I experience every time I give that class, people take the projection because we are only dealing with 2-dimension. So when you take the 2-dimension, it's going to look like this, a center line in the middle. This is R. This is a vector R. So R equals 0 here. R is equal R capital here. R is equal minus R capital. There is heat generation in the fuel. There's heat generation here. That's K of the fuel. So sometimes people get confused about between this and the plate type. This is R, is no longer X. Okay. So again, you will find, I don't want to go in details. We can only deal with only one side because of the symmetry. We will have also a second order temperature distribution with maximum temperature at the center line. We're going to call that T surface. And there is quantity of heat removed from that face here. We call that QS. Going quickly, what is the governing equation? It's 1 over R, partial by partial R partial T by partial R plus Q dot over K equal 0. That's a cylindrical coordinate. Then you can integrate the equation to get a formula for the temperature distribution. It's going to be T as a function of R equal to minus Q dot over 4 K of the fuel, whereas that thermal conductivity of the fuel, times R squared plus C1 natural log of R plus C2. Then you have to apply boundary condition. You will end up having T as a function of R is equal minus Q dot over 4 K of the fuel plus times R squared plus T max. This is very similar equation to what we got for T of X, right? Then you can get Q. It will be also a function of R. It will be Q dot times the volume, which is pi R squared L. Depend on the value of R. If you want to get QS, you put R equal R capital. So QS will equal to Q dot pi R squared L, whereas R is the outer radius of the fuel itself. So again, this is the Q dot times the volume of the fuel. Then we can drive the an equivalent resistance for what we need. So we can actually have now, I can draw half of it. Again, I'm just going quickly here. You are not obligated to look into it. So that's the fuel. This is R. This is R capital. Temperature distribution is second order. This is Tm. This is Ts. And there is Q dot. There's K of the fuel. We can drive a R thermal conduction. This case is in cylindrical fuel shape, is equal to 1 over 4 pi K of the fuel times L. So that's the equation that we use for cylindrical fuel shape as a thermal resistance. Okay, so now I can replace this by a thermal resistance between T max and T surface. That heat is going out is QS, which is going through the resistance. And this is the R thermal conduction, which is calculated from this equation. Okay. So if I give you the following schematic here. This is E fuel. This is E cladding. And I'm surrounded by a coolant. So this is T infinity and H. That's a coolant. This is R. This is the R capital. I'm going to call that thickness here cladding. This is K fuel. This is K cladding. There is heat generation here. Okay. Then I would like to draw the thermal circuit that present that case. We know that for the fuel, I'm going to have second order. That's Tm. I'm going to call that Ts. This is called T cladding. This is cylinder. Don't tell me this is linear. It's not linear. It is what it is. Could be a curve. Like this. Okay. Then we have the coolant. I forget last time to mention how to present the temperature distribution in convection. It is simply decreasing of the fluid and flatten out, and this should be the T infinity. So that's how we present the convection temperature distribution. So going back to the thermal circuit analysis, I will have T max. I will have T surface. I will have T cladding. I will have T infinity. 3 resistances here. This is for the fuel. This is for the cladding. This is for the coolant. And all of them, I'm having QS going through. QS is what's leaving the fuel, but it's going to continue all the way to the end. So how we calculate the fuel resistance? R fuel, the equation is 1/4 pi K of the fuel times L, whereas L is the length of the cylinder. Okay. Then next, I want to let's do the R convection first. R out. It's 1/H times A. What is A? A, it's pi times D times L. I want to get what is this diameter here? What is the convection happening? The convection is happening here. What is that total radius? Or you can write that 2 pi RL. That's 2 times radius. And the radius where the convection is occurring is R plus C. So if I multiply that by 2, this should give me the diameter I need for that convection. Keep in mind the convection is happening at the very outer face. This is simply like this. This is a solid cylinder that's presenting the fuel. This is the cladding. And the convection is happening outside here. This is the coolant. So this is R. This thickness is C. So the convection is happening in R plus C. That's what you need for the convection. Now, let's get the R for the cladding. This is a cylinder. So the equation is natural log of R out over R in divided by 2 pi K cladding L. Now let's define the outer and inner radii here. What is the outer radius in that problem? The conduction is happening between here and here. So I need that outer radius here, and this is the inner radius here. So the outer one is R plus C divided by R. That's a ratio. Okay, and this is L. Then you can calculate QS from picking any 2 temperatures. Let's assume that I give you T max minus T infinity. You have to divide by R fuel plus R cladding plus R of the coolant. Then you can use this one to get T surface, for example. So it's going to be T max minus T surface divided by R fuel. I can get T surface out of this equation. Then if you want to get T cladding, you can take the same Q, say this is T cladding minus T infinity divided by R out. There is one note here I need you to be aware of. What if this T cladding? What if the L is not given? If L is not given, You assume it's unity. We assume is unity. So L equal 1 per unit length. So we got everything per unit length. So you can actually delete L from this equation. You can delete L from this equation. You delete L from this equation. So sometimes instead, because we don't know the length, so we can actually call RF prime, R convection prime, and R cladding prime. And that QS will become QS prime, everything per unit length, okay? If we go back to the plane wall, if the area is not given, you assume it's 1. So sometimes we call, let me go back to that page. The last one that we show the case study. Like in here, what if the area is not given? You drop the area, assume it's unity. So if A is not given, you assume it's 1, which means that we are getting everything per unit area. So sometimes we call R fuel double prime, R cladding double prime, R convection double prime, and the QS becomes QS double prime. So you got actually the flux. So just keep that in mind. Sometimes L is not given, sometimes the area is not given. You can drop them and you simply calculate everything per unit length, or you calculate everything per unit area. So that's happening. And these are the Q prime, Q double prime that we defined early at the beginning of the class. So the last piece now is to actually look into the spherical shape, okay? You realize that convection resistance does not change. The only one that we keep it changing is the conduction when you have Q dot. That's it. So we did learn Q dot for plate type fill, for cylindrical fill. What about the spherical fill? I'm not going to go through the equation. I'm going to give you the equation right away for the spherical shape fill type, which is the pebble type 1. So the equation will be actually R fuel for a spherical shape, the conduction. This is the conduction resistance is simply equal to 1/8. Let me write it down correctly. 1/8 times pi times the K of the fill times the radius of the fill. So this is the radius. Let me draw it actually. That's a spherical fill shape here. This is the R capital, and this is the vector R. So this is radius of the sphere. And this is the equation that we're going to change for conduction. Then the convection remain the same. Nothing would change actually. And the conduction, if there is a cladding, that's where Q dot is, and KFL, that's the fuel. Then the cladding, we use the same equation that we used before for conduction in a cladding without heat generation. So go back to the last class and look into this. So I have a good summary here that's summarizing all these kind of equations. I'm going to show it to you here, and it's going to be actually in the material I'm going to share. So we have plate type fill, we have cylindrical type fill, we have a spherical type fill. Okay, Q always is function of X, function of R, function of R. Okay, so it's Q dot times AX, Q dot times pi R square L, Q dot times 4/3 pi R cube. R is a vector, R is a vector, X is a vector. Now, if we need to calculate how much will be dissipated from the outer surface of the plate, cylindrical or spherical shape, we put X equal half the thickness of the fuel, put R equal the radius of the cylinder, you put R is the radius of the sphere. So that's the quantity of Q that's going to go through the thermal resistances. Okay? Then I'm listing here all the resistances. This is the fuel. This is where Q dot is. This is where Q dot is. This is where Q dot is. The rest are just the resistances that we did learn before without having heat generation. So these are the new resistance when you have a heat generation. And these are the old cases that we have. So I combined all the resistance in this sheet, which you can use to solve your homework assignment or quizzes or anything like that. So you don't have to memorize it, but it is very important to understand how to use this equation, when I use this equation. And please avoid any confusion about when you see the two-dimension drawing. Is it like this? What geometry is this? This is plate or this is cylinder? It depends. If this is X, I'm talking about plate. This is R, I'm talking about cylinder. So you have to stick to the right resistance that you need to use. I think the next step is actually start having some little bit of exercise. So I think I'm gonna pick a problem or two just to show you how to apply these equations. So I will cover that in a next report.